Okay. All right, thank you all. We're down to our final two presentations. Up next is Matteo Basso from CSCS.
Good afternoon. I'm Matteo Basso, IT security engineer at CSCS, and I will present a practical security blueprint for modern software-defined HPC system as our CSCS Alps at CSCS. Everything is based on real production experience at CSCS, and the focus is not theory, but what works in practice when the security teams are small, as our team, the systems are large, as Alps, regulatory pressure is real. So the agenda for today is pretty straightforward. We'll start with the security architectural shift happening at CSCS in our HPC and why to fundamentally change the security problem. So we walk through the operational constraint we faced and the resulting security architecture and how it's implemented in production. Finally, as usual, some conclusion and future vision. So security challenges at CSCS in our HPC today are not incremental changes to the old model, but they are something new. They are driven by a deep architectural shift in how the systems are built, operated, and governed. And this forces us to rethink a long-standing security assumption. The HPC is moving from a static monolithic cluster to our dynamic ecosystem built from software-defined tenants, pipeline, and services. This dramatically increased both the attack surface and the operational complexity. At the same time, performance remains non-negotiable, and the compliance expectation now demand audible evidence. The blueprint I propose embeds security directly into the infrastructure as code or infrastructure service workflow to make this viable at scale. So the requirements are security must be dynamic and version as the infrastructure itself, because dynamic, we are able to tailor based on specific need the baseline. Version, because everything is tracked and reproducible with the solution is infrastructure as code or infrastructure as service. Historically, at CSCS, HPC security worked well because the architecture for us was simple as security. It was a fortress, so few jump posts, no SMH spread across all the nodes, one CV surface, and a narrow threat model. So basically, SSH brute force, credential stealing. Now we have a fleet of independently configured vCluster, and I will explain later what is a vCluster. Each vCluster may contain different packages, user, and purpose. Each vCluster evolves differently, and the CV surface grows and fragments. Plus, we have a new risk, a supply chain risk, based on infrastructure as code and infrastructure service pipeline. And last but not least, we have a multi-regulatory policies based on vCluster. In any realistic HPC center, the HPC security model must start from an operational reality. EV agents on nodes, login or compute are often unacceptable. A centralized SOC system don't scale, and the platform team who run the vCluster need autonomy. At the same time, the incident response and compliance evidence are mandatory, and this creates some kind of tension between the security, the performances, and the productivity. Our response focuses more on automation, selective instrumentation, and distributed responsibility. So these constraints force us a shift not just in tooling, but in how we think the threat model and responsibility boundaries in HPC. And before moving, I will explain the vCluster model. So CSCS Alps use a versatile cluster model, which is a tenant-specific cluster defined entirely through code and deployed on shared bare metal hardware. The images are immutable and versioned, the service evolves independently, and the vCluster can be created or decommissioned on demand. From a security point of view, heterogeneity and the constant changes become a first-class design input for us. So the security must be designed to handle diversity and constant changes. This impact of the vCluster is pretty, not simple, but straightforward for us. So there is no single security baseline anymore. because we can have different OS, different kernel version, different package installed, and each of them can create a different CVE baseline. The controls are no longer universal because we can run in vCluster different intrusion detection system, different file integrity monitor or benchmark, and we must tune the baseline per vCluster. So one baseline fits all is no more working, and because we can create a lot of noise or miss some issue in other situation. Even the delegated access control becomes a security boundary that must be monitored and audited across the entire fleet. The security is no longer global, but it becomes per vCluster, and it's continuously evolving. The supply chain risk I was mentioning before is because the infrastructure as code, infrastructure service workflow into the DevOps model make the software-defined HPC at CSCS operationally possible, but it centralizes critical artifacts in a shared pipeline and repository, and it creates a supply chain blind spot for us. Because also modern dependencies are deeply nested, often 5 or 6 level deep, and these sub-libraries frequently suffer from fragmented CVE visibility. A traditional scanner failed to map this vulnerability hidden deep in the stack, so the idea is shifting the control earlier as possible using SBOM or pre-deployment scanning to audit the full stack before it even hits the fabric. Security controls must scale horizontally with infrastructure, not with the team size. The automation and the standardization must ensure controls are applied consistently. The teams who is running the vCluster retain the autonomy, while the security, so us, maintain the visibility through the shared tooling. And the last thing is evidence is produced automatically as part of normal operation. So we are not doing something out of the box. With this, we wrote our architectural principles, which are concentrating the controls where they matter, limiting the compute and login node overhead, accepting integration complexity, and prioritizing the fast risk reduction over the perfect immutability when needed. To address this, we designed the security architecture of around few core principles rather than some isolated tools. Our architecture consists of tightly integrated layers. First of all, there is a security vService, which is basically a kind of automation tool to install some software and a rapid patch pipeline. A SIEM platform for aggregating and correlating the events. The vulnerability management, which is a centralized system for scanning and tracking weakness. And a compliant validation tool, which are some executable tests integrated into some framework. On the HPC user side, we installed and used the compliance services, the SIEM and vulnerability management, plus the vService, because there are the vCluster. On the engineering side, so on the Alps management plane, we are just running a SIEM and a vulnerability management. I will now briefly move on the components. The first one is the security vService that automates the security bootstrapping during the provisioning of the vCluster, and it supports the remediation for zero-day vulnerabilities. We are using it for basically install and configure the Wazoo and Tenable agents, which are our SIEM and our vulnerability management tool. Plus, there is the rapid critical patch pipeline, which is a pipeline that we use when there is a zero-day coming and in our login node. So if we find a zero-day, we are able to upgrade and update the package in minutes instead of recreating the image, redeploying the image, recreating the vCluster, having downtime, and blocking some jobs. Everything from the security vService is easily reproducible with an Ansible playbook, and at the moment at CSCS it handles 11 vCluster and 13 login nodes. The CM, we selected Basso as CM because it provides for us a single lightweight agent suitable for the HPC environment. The agent overhead on the login nodes is 1-2% of the CPU. We're just using it on the login nodes, not on the compute node. It's open source. It has a huge community behind, and a lot of new features are coming weekly or monthly. It's based on OSSEC, and it allows us to create custom rules, custom detectors, custom integration, so we are able to basically ingest all kind of data we want into it and correlate all the possible events. In practice, our CM or Basso acts as the central nervous system. It aggregates the events, the correlated detection, and is able to route the alert to us as security team plus the team owner of the vCluster. We can create and deploy dashboard for the vCluster team. Over that, is able to detect and respond to some kind of attack, for example, the SSH brute force attack or file integrity monitoring. So a file changed by a user and monitor. These, the active response helps us because we are able to block the IP, for example, or send an email if the user is changing a file. And it's pretty useful if you don't have a 24 hours environment. The main reason for selecting Basso is we are able to tailor the configuration per vCluster. So each vCluster may have or can have a baseline. And as I said before, to reduce some noise or to add some kind of controls instead of having just one baseline for all the vClusters. Out of the box, Basso is able to be helpful for some compliance as HIPAA or GDPR, and we were able as well to create our personal compliance check for NIS2, and it's something really useful to be able to create something customized for us. For the vulnerability management part, we are using Tenable.sc. As part of ETA, we can have a small tenant for us. The idea behind is know what you have, then fix it, because we are focusing on authoritative scanning and time series per vCluster, and we are able to identify, of course, the vulnerabilities on the login node. We are integrating all the data into the CM because we are able to ingest all the data. And the main reason for having a vulnerability management as Tenable is because we are able to do a static and runtime vulnerability check. The static one is, okay, we are running statically when we deploy the image or when we have the new vCluster and we are able to identify vulnerabilities. The runtime scanning is required because Tenable is able with some plugins to detect configuration, file misconfiguration, or parameter changes. Maybe a user is changing a file, changing a configuration, and after that, the software may be exploitable. So Tenable is helping us also in this situation. For the compliance, as a code, we are implementing it as executable test using the Reframe framework, as Victor mentioned before. All the controls are validated continuously and integrated into some CI/CD pipeline, maintenance, and audit workflow. These produce for us some deterministic and reproducible evidence instead of having a manual checklist. As control, we are using the ANSI BP 028, the stick DoD, and some custom checks written for our vCluster and at CSCS. This architecture helps us a lot also for the Swiss ISA, the NIS2 and the Cyber Resilience Act, and position us well for ISO 27001. The key lesson here is the trust comes from continuously generating inquirable evidence, not from reports written after the fact. And as last piece of this presentation, I will describe a practical example of our architecture, so a real-world use of our architecture. A few months ago, the Munge package was affected by a CV, the 25506. It was a buffer overflow vulnerability. A locker attacker could exploit this vulnerability to leak some cryptographic key used by Munge from a process. They were into the memory. So the first thing was understanding if our vCluster were affected. We checked our CM to determine whether the CV was present in any vCluster. We found a login node. Okay, now we have to double check if the data were properly ingested into our CM. So we double check in Tenable. We found the same vulnerability. We checked again in our CM in the AT hygiene board to check if the version was the one affected by the CVE. We found it. With the security vService critical patch pipeline, we were able to patch the login node in minutes, and they recreated the whole vCluster later. But for us, the vulnerability was basically done, and we were able to move on and be more secure in that day. As a conclusion, we have some key takeaways for us. This blueprint documents our real security posture at CSCS in a production scale environment. The main challenge for us was integration rather than the tool selection, and the unified operationalizing view enabled the full context per node. Embedding the security into some engineering workflow make it sustainable for our team, because we are not a huge team, so we were able to do it. And as future work, we want to focus on formalizing processes, extending the control upstream into the environment, deepening the CM integration correlation with other tools as Kubernetes or storage appliance and network telemetry, and plus consolidating our reporting Grafana, integrating the Marmot graph, as Massimo mentioned before, trying some RAG-driven security inside, and integrating the BPF into the vService, as Victor mentioned before. And that's basically everything. If you have any question, otherwise, thank you.